Okay, let's unpack this. We are diving deep, like right down to the atomic level today. We're looking at the two most profound energy sources we know, nuclear fission and nuclear fusion.
Yeah, these are, huge topics. They sound super complex, maybe a bit intimidating, but they really govern everything from, like, the power grid keeping our lights on
Right.
all the way up to the sun. Its entire engine.
So our mission today really is to cut through that complexity. We want to get clear on splitting atoms versus joining them. What's the real difference? And, really understand why that famous equation EMC4 is just so fundamental.
Exactly. It's like the universal language of energy, isn't it? And for this deep dive, we've drawn on some really great physics material, sources that focus not just on the what, but the why, the human story behind it all.
Which is crucial because the story, especially for fission splitting the atom, it's full of drama. And you really have to start with Lise Meitner, don't you?
Oh, absolutely. She's central, an incredible scientific pioneer. Born Vienna, 1878, she was actually the first woman to get a doctorate in physics from the University of Vienna back in 1906.
Wow. And then she moved to Berlin.
Yep, worked with Max Planck for a bit, then started this amazing 30-year collaboration with Otto Hahn. Around 1907, they teamed up. Radiochemistry, she was the physics brain, he handled the chemistry side.
And they discovered an element together, protactinium.
That's right, in 1918, a really productive partnership. But then things got dark by the late 30s.
Right, the political situation in Germany.
Exactly. Meitner had Jewish heritage. So tragically, she was forced out, had to flee Nazi Germany in July 1938, ended up in Sweden.
And this is where it gets kind of wild, historically speaking, because while she's in exile in Stockholm, Hahn and another scientist, Strassmann, they're back in Berlin doing these experiments.
Right. They're bombarding uranium with neutrons, standard stuff at the time, trying to create heavier elements.
Right.
But in December 38, they look at their results and they find barium,
which is much later than uranium, right?
way lighter, about half the size. They were completely baffled. It made no sense based on the physics they knew. How could you hit a heavy nucleus and get something so light out of it?
They couldn't explain it themselves?
Nope. They knew it was something big, something new, but they were stuck. They even wrote to Meitner about it.
So the insight came from her while she was in exile.
Yes. She got Hahn's letter, discussed it with her nephew, Otto Frisch, who's also a physicist, and visiting her for Christmas. And over that holiday, walking in the snow apparently, they figured it out.
What was the breakthrough?
Meitner realized the uranium nucleus wasn't just getting chipped or slightly changed, it was splitting, violently splitting in two, kind of like a biological cell dividing was the analogy they used.
That's incredible. And Frisch coined the name.
Yeah, he called it fission.
Yeah.
And the irony is just staggering. She's forced out of the country, loses her lab, everything. And then she solves perhaps the biggest physics puzzle of the century from Sweden based on her former partner's confusing results.
Okay, so let's nail down the mechanics then. Fission is splitting a heavy nucleus, like uranium-235, right?
Man.
It gets hit by a neutron.
And it splits into two smaller nuclei, the fission products, often things like krypton and, well, barium, as Hahn found. Plus, critically, it releases several more neutrons, usually 2 or 3, and, of course, energy.
A lot of energy. The sources mentioned something like 200 mega electron volts.
Yeah, 200 MeV per single fission event, which sounds abstract, but compared to a chemical reaction like burning fuel, it's about 20 trillion times more powerful per atom.
Okay, pause there. Where does that energy actually come from? It seems to appear from nowhere.
It comes from mass. This is the EMCF part. It's called the mass defect. If you could weigh everything before the split, the original uranium nucleus plus the neutron that hit it, and then weigh everything after the split, the two smaller nuclei plus the new neutrons released.
Let me guess, the after weight is less.
Exactly. Slightly less. Just a tiny fraction of mass seems to have vanished. But it didn't vanish. It was converted directly into that massive burst of energy. Mass is energy.
Mind-blowing. Okay, so one split releases tons of energy. But making that useful, sustaining it, that's the next step, right?
That's the key. And it comes back to those extra neutrons that are released. For the reaction to continue, those neutrons have to go on and hit other uranium-235 nuclei, causing them to split too.
Ah, the chain reaction.
Precisely. And for that chain reaction to sustain itself, you need enough fissile material packed together. You need what's called a critical mass. Otherwise, too many neutrons escape without hitting another nucleus, and the reaction just stops.
Got it. And this whole chain reaction idea, that became the focus of the Manhattan Project during World War II.
It did. But an often overlooked milestone was actually the first controlled, sustained reaction. Not a bomb, but controlled power.
Yeah.
That happened December 2nd, 1942, under the stands of a football field in Chicago.
Seriously. Chicago Pile 1.
Yep, led by Enrico Fermi. They proved you could actually control fission, throttle it up and down. Huge moment.
But using it reliably is tricky because of the materials, right? Natural uranium isn't ideal.
Not really. Most of it, like 99.3%, is uranium-238, which doesn't fission easily with the kind of neutrons produced. Only about 0.7% is the U-235 isotope that we need for most reactors. So you need to enrich it, concentrate the U-235.
Or use plutonium.
Or use plutonium-239, yeah.
Right.
Which is actually made from U-238 in reactors. Plutonium works very well, used in weapons and power.
So let's talk applications. Fission clearly has big advantages for us today.
Definitely. Nuclear power plants using controlled fission generate a massive amount of electricity. And a key benefit, especially now, they don't burn fossil fuels. No CO2, no SO2, none of the greenhouse gases driving climate change.
That's huge. Reliable, carbon-free energy on a large scale.
It is. But there's always a but, isn't there? The waste. That's the major challenge. The fission products, the spent fuel, it's highly radioactive. And some of this stuff stays dangerously radioactive for thousands, even hundreds of thousands of years.
So we have this incredible power source, but it leaves behind this toxic legacy that we have to manage, essentially forever.
Pretty much. Safe disposal, long-term storage. It's a massive ongoing global problem. And the risk of accidents, though low, is catastrophic when it happens.
Okay, so fission. Powerful, practical for electricity, zero carbon emissions, but with this really difficult long-term waste issue. If that's splitting atoms, let's pivot to the opposite. Fusion, joining atoms together.
Right, fusion. Think of it as the cosmic engine. It's what powers the stars, including our sun. Instead of splitting heavy nuclei like uranium, fusion takes very light atomic nuclei isotopes of hydrogen, usually, and smashes them together.
To form a heavier nucleus, like helium.
Exactly. Deuterium and tritium, which are heavy hydrogen isotopes, fuse to form helium, plus a neutron, and again, energy.
But smashing positively charged nuclei together, they'd repel each other, right? Like trying to force two north poles of magnets together.
Precisely. The electrical repulsion is enormous.
Yeah.
To overcome that, you need insane conditions, temperatures of millions, even hundreds of millions of degrees Celsius, and incredible pressure.
Thermonuclear conditions.
That's the term. Conditions like you find in the core of the sun.
And the sun just does this constantly on a ridiculous scale.
The numbers are hard to grasp. Our sources say the sun fuses about 657 million tons of hydrogen into helium every second.
Wow.
And in doing that, about 4 million tons of its mass disappears every second, converted directly into the energy that lights and warms our planet. Again, ETMMCO.
Okay, so help me connect this. Fission splits heavy things, releases energy. Fusion joins light things, releases energy. Why do both processes release energy? It feels counterintuitive.
It does seem weird, but it makes sense if you think about nuclear stability. There's something called the binding energy curve. Think of it like a graph showing how tightly bound the nucleus of each element is. Iron-56 is at the peak. It's the most stable nucleus there is.
Okay, iron is peak stability.
Right. Now, the very heavy elements like uranium are less stable than iron. They're up the slope on one side. So when uranium splits, fission, the pieces it forms are closer to iron, more stable. That difference in stability is released as energy.
Okay, so fission rolls down the curve towards iron. What about fusion?
The very light elements, like hydrogen isotopes, are also less stable than iron. They're up the slope on the other side. When they fuse together, fusion, to form something heavier like helium, they're also moving closer to that iron peak of stability.
So they also roll down towards iron just from the other direction.
Exactly. Whether you start really heavy and split or start really light and join, the end products are more tightly bound, more stable. Both processes move towards the most stable configuration, iron, and release the excess energy that was holding the less stable nuclei together.
That makes sense. It's all driving towards stability.
That's the fundamental physics behind both.
Now, on Earth, we've managed uncontrolled fusion, right? The H-bomb?
Yes, sadly. The hydrogen bomb, first tested in 1952, it basically uses a fission bomb, an A-bomb, just to create the intense heat and pressure needed to trigger the fusion reaction.
But controlled fusion, like for power plants, that's the dream, isn't it?
It's the holy grail, really. The potential is immense. The fuel deuterium from seawater, tritium bred from lithium, it's incredibly abundant and cheap compared to uranium.
And the waste.
That's the other huge potential advantage. Fusion doesn't produce the same kind of long-lived, highly radioactive waste as fission. The main byproduct, helium, is harmless. There's some activation of reactor materials, but it's generally shorter-lived.
So abundant fuel, much less problematic waste. Sounds perfect. Why don't we have fusion reactors powering cities already? The sources seem a bit cautious, calling it maybe a dream for the future.
Because it is unbelievably hard to do technologically. We need to heat fuel to temperatures hotter than the core of the sun.
Okay.
And then we need to contain that super hot electrically charged gas called a plasma without it touching the reactor walls, which would instantly cool it and vaporize the wall.
How do you even contain something that hot?
Usually with incredibly powerful magnetic fields. Tokamaks and stellarators are the main designs. We can achieve the temperatures. We can contain the plasma for short periods. We've even generated more energy out than we put in briefly in experiments like JE and F.
But not sustain reliable power generation.
Not yet. Maintaining the stability of that burning plasma long enough, extracting the heat efficiently, developing materials that can withstand the intense neutron bombardment for years. These are massive engineering hurdles. We understand the physics pretty much. But building a commercially viable power plant, that's still a monumental engineering challenge.
So, wrapping this up, we've journeyed from Meitner's insight into fission
Through the chain reactions, the power plants, the waste problem,
to the cosmic power of fusion, the sun's engine.
and the immense challenge of trying to bottle a star here on Earth.
Fission gave us usable, controllable nuclear power, but with that significant waste drawback. Fusion offers this tantalizing promise of clean, almost limitless energy if we can just figure out the engineering.
Right, and both, fundamentally, are just tapping into that mass energy conversion described by you in AMC4. Two sides of the same cosmic coin, driving towards nuclear stability.
Understanding this difference, fission versus fusion, it's pretty critical, isn't it, for understanding energy policy, climate solutions, even future tech.
Absolutely. Fission is the technology we have now, providing significant carbon-free electricity, despite the challenges. Fusion is the potential future, the hope for something even better.
Which leads to maybe a final thought for our listeners to chew on. The sources highlight this contrast. Fission relies on relatively scarce, enriched uranium or plutonium and creates waste that lasts millennia. Fusion fuel is abundant, and the waste issue seems much more manageable, at least in theory.
So the question that lingers, and it's a big one raised implicitly by the material, if the fundamental physics of fusion is sound, if the fuel is everywhere and the waste is less of a nightmare, is achieving practical fusion power just an incredibly difficult, incredibly expensive engineering problem that human ingenuity and investment will eventually solve? Or is there some deeper, perhaps unforeseen physical barrier or complexity that we just haven't quite grasped yet, making it fundamentally harder than we currently think?
Is it a matter of time and will, or is there a hidden hurdle, something to think about?